Now let's discuss stability from input-output relationships. We say a system is stable if every bounded input yields a bounded output. We say the system is unstable if any bounded input yields an unbounded output. So we call, in this case, a system is said to have bounded input for bounded output. It is called BIBO stable. BIBO stability. If every bounded input results in a bounded output. We know the output of a linear time invariant system can be written as the convolution integral of the impulse response and the input. So here is a convolution integral, and h tau is the impulse response, and u t minus tau is the input. Based on the definition we know, let's test the stability. Since we know input signal is bounded, let's assume the absolute value of the input signal is less than a constant m is less than infinity. Therefore, the input signal is bounded. Then, based on the equality, so the absolute value of yt is the absolute value of the convolution integral. Then, based on the inequality, we can move the absolute sign inside the integral. So it's less than or equal to the absolute value of impulse response times the absolute value of the input signal. Then we know input signal is less than m, so the absolute value of the output signal is less than or equal to m, the integral from 0 to t absolute value of the impulse response. Therefore, we know to have bounded output, if we can bounded the integral of impulse response, the absolute value of the impulse response. Then we have a mathematical definition. A system with impulse response ht is BIBO stable if and only if the integral from 0 to infinity absolute value of impulse response is less than infinity, because we need t approach infinity. So here is a condition from the impulse response to guarantee the system is BIBO stable. Now let's look at an example. We have a capacitor. Capacitor is driven by a current source. Well, the capacitor voltage is output and the current is input. As we did as usual, let's written the capacitor in impedance form. So it's 1 over Cs. Then we know the transfer function from Us to Ys, that is Ys output, the voltage across the capacitor, input is a current, Us. We know based on the Kirchhoff voltage law, so Ys 1 over Cs times Us. Then Ys over Us is 1 over Cs. If we take inverse Laplace transform, then we know the output value. So we know 1 over S, it is an integrator. So Yt will be integral of u tau d tau. Therefore, the impulse response, the transfer function is the impulse Laplace transform of the impulse response. So if we take the inverse Laplace transform, then we can get the impulse response. If we take the inverse Laplace transform to the transfer function, we get impulse response. That will be 1 over C. Then my question to you is this system BIBO stable or not? I will give you a few minutes to think about it. then we can use the mathematical definition to verify if the system is BIBO stable or not. So the integral from 0 to infinity, the absolute value of the impulse response is the integral from 0 to infinity, the constant 1 over c. Then we know it is infinity. Therefore, the impulse response is unbounded. Therefore, we know it is not BIBO stable, since the impulse response does not approach to 0. It is also not stable from the impulse response perspective. So now let's discuss the BIBO stable and the pole locations. Can we use the pole locations to guide the system is BIBO stable or not? Now the first case, an LTI system has any pole on the imaginary axis. I will give you a few minutes to think about it. If a system has any pole on the imaginary axis, is the system BIBO stable or not? Now let's assume a system with transfer function 1 over s by s over us. Let's see if this system BIBO stable or not. So to test it, we can assume the input is step signal. Let's assume US is a step signal, the unit step signal. Then we know the Laplace transform of a unit step signal is 1 over s. We know the output, Laplace transform the output 1 over s times US, then 1 over S squared. Then if we apply the inverse Laplace transform, we get ut is t. It is unbounded. Therefore, an LTI system has any pole on the imaginary axis. The system is not BIBO stable. Now let's consider another case. So let's assume the transfer function has s plus s squared plus p squared. So we know it has a pair of complex, a pair of imaginary poles, p, j minus p, j. So if in this case, if we have input signal is sinusoidal wave, if we have with the same frequency, sine pt, then if we apply the Laplace transform, say this is ut, then if we apply Laplace transform, we will have p s squared plus p squared. Then ys will be 1 will be us times transfer function then we have us here, then have p s squared plus p squared then squared. So in this case, since we have repeated, you see we have repeated poles, then the time response, we need to multiply t. So yt will be have some form like t sine pt. It will grow unbounded. Therefore, an LTI system has any pole on imaginary axis. It is not BIBO stable. Now let me give you a few minutes to think about the second case. An LTI system has any pole in the right half plane. Is this system BIBO stable or not? Again, let me give you an example. Suppose the transfer function is one over s minus one. We know the impulse response is the inverse Laplace transform of the transfer function. Therefore, the impulse response ht will be exponential t. Then if we integral 0 infinity to ht up to the value of ht dt, definitely it will be unbounded. Therefore, an LTI system has any pole in the right half plane. It is not BIBO stable. The last case, an LTI system. For an LTI system, every pole is in the left half plane. Is the system BIBO stable or not? Again, if every pole is in the left half plane, then it will be in the partial fraction expansion to have s plus pi. So pi is greater than 0, the real part. Then therefore, the inverse Laplace transform, it will be exponential minus pit. That will be the impulse response will be a sum. If every one of such terms, let's verify if they are bounded or not. The integral from 0 to infinity you can verify that if the real part of pi, is less than 0, then the integral is less than 0. less than infinity, sorry, so less than infinity. Then we know the system is BIBO stable. Now let me show you an example. We have two systems. We have the open loop system. They have the same poles. Poles will be 0, -1, and -7. So let me ask you this question. Is the open loop system stable, marginally stable, unstable, BIBO stable, or not? From impulse response perspective, the system is marginally stable. Since it has poles in the imaginary axis, it is not BIBO stable. The two systems, they have the same input. The input signal, the unit step signal, is bounded. Then we use the unity feedback to see if the output, then the closed loop system is stable, unstable, marginally stable, BIBO stable, or not. We know the open loop system is marginally stable, not BIBO stable. Then when we look at the closed loop system, in this case, the closed loop system have outputs to calculate the transfer function for the closed loop system. Then you need to use the block diagram reduction, and in the case of the feedback arrangement. In this case, the poles in the closed loop system, they're all in the left half plane. Therefore, the closed loop system is stable. It means the feedback can make a marginally stable system stable. We see the output is also bounded. The open loop system is not BIBO stable for the unit step input, but for the same input, the closed loop system is BIBO stable. For the second case, we still use the unity feedback, but in this case, the closed loop system, the poles will be in the right half plane. Therefore, the closed loop system is not stable, not BIBO stable. You will see for the same step input, unit step input, the output is unbounded. You see the only difference is the gain. as I mentioned in chapter 1, feedback can make an unstable system stable, but if the feedback gain is too large, it can make the system unstable. That is the case. Therefore, we know an LTI system, linear time invariant system, is stable. Stable from the impulse response, or stable, or BIBO stable. If all the poles of the transfer function have negative real parts. That is, all the roots of the denominator polynomial are all in the left half S-plane. If all the poles are in the left half S-plane, we call the system is stable. It's both stable from the impulse response or from the BI input-output relations. But actually, they are the same. So the BIBO stable is equivalent to stable in the impulse response sense.